So today we have two problems to solve. The first one is, as you can see now, we have simple beam AC, and we have two applied load, uniform load 3 kN per meter, and point load at B 10 kN. And we want to draw shear force diagram and bending moment diagram. This is the first requirement. Second requirement, we need to indicate the location and amount of maximum moment, max. Okay, so we have these two requirements for each equation. Okay, I will now start solving this with you. So I will share the other screen. I will check all the received quizzes after the class, and then if I didn't receive from someone, I will ask him to send again. Okay, I'm now sharing the other screen. Can you see the screen now? The big screen. Okay, today we have same type of problem we have done last week. So we have a simple beam, and here we have support, hinged support at A, and we have a roller support at B, at C. Okay, and we have a uniform load Q small equal to 3 kilonewton per meter, and we have 10 kilonewton applied here, B equal to 10 kilonewton. At point B, the dimension of the beam is R 6 meter from A to B and 2 meter from B to C. Okay, the requirement again, we need to draw shear force diagram and bending moment diagram. This is the first one. Second one is location and value of max, which is the maximum moment of this beam. Okay, so this is the two requirement we have, and we need to draw the bending and shear force diagram. Okay, so now what is the first step to solve this type of problem? The first step is to find the reaction or determine the reactions. How many reactions we have for this problem? Here we have hinge, so we have YA and XA, and we have YC. So this we have three reactions. If we apply the equations, we have summation X equal to 0, so XA should be 0. So XA 0. Next, second equilibrium equation is summation moment at A. Before we apply summation moment at A, what we need to do? We need to concentrate the uniform load because we can't deal with the uniform load like that. So we need to concentrate it. So I will concentrate this part itself and this part itself. Why I divide or subdivide the uniform load? Because we have a point load at B disturbs the continuity of the uniform load. So if you have a point load in the middle or disrupt the uniform load, you have to concentrate each part itself. So you have to concentrate from A to B and then from B to C. So from A to B, the length is 6 meter and the load is 3 kilonewton per meter. So the load will be 18 kilonewton. And for this part, from B to C, we have 2 meter and 3 kilonewton per meter. So it will be 6 kilonewton. So this is the all load we have. We have 18 kilonewton and 6 kilonewton plus the 10 kilonewton point load. So now, and before we go to the next step, where this loads apply? As you know, the uniform load, the resultant of the uniform load will be in the middle. So this will be 3 meter and this will be 3 meter. Here as well, the resultant in the middle, so 1 meter and 1 meter. Now we can apply the moment equation. If we apply the moment at A equal to 0, what forces cause moment? YC rotate in this direction, 6 kilonewton rotate in this direction, 10 rotate in this direction, and 18 rotate in this direction. So if we start with YC, so YC multiplied by the distance, how much is the distance? 8 meter, and it is rotating anti-clockwise, so it is positive. Minus 6 multiplied by the distance is from A to this load, 7 meter, rotating clockwise, so negative. 10 also rotating clockwise, so negative 10 multiplied by the distance 6 clockwise. Then we have minus 18 also clockwise multiplied by the distance, which is 3, should be 0. So this is the forces cause moment at A. From this equation, we can find that YC, the reaction at C, equal to, can you calculate it with me? If we do the calculation, so we have 19.5. So the reaction YC is plus 19.5 kilonewton. What does the plus sign mean? The plus sign means this reaction is going up because Y positive up. So YC equal to 19.5 kilonewton. So to get YA, we apply the third equilibrium equation, summation Y equal to 0. So we have how many loads in Y direction? We have YA, YC, 6, 18, 10. So if we apply this equation, we have YA going up positive plus YC 19.5 going up positive minus 6 going down minus 10 going down minus 18 going down. This all together should be 0. From this equation, we can find that YA equal to 14.5. So the reaction at A is 14.5 kilonewton. The positive sign means this reaction is going up. Okay, so this is our reactions. YA equal to 14.5. Do you have any problem with the reaction for this beam? Okay, now we go to the second step. Is drawing. Draw shear force diagram and bending moment diagram. So if this our beam and we have here support A and support C. The reaction here was 14.5 kilonewton and the reaction here is 19.5 kilonewton, and we have uniform load 3 kilonewton per meter, and we have 10 kilonewton per meter here. The dimension are 6 meter and 2 meter. We have concentrate the loads here 18 kilonewton and 6 kilonewton. So to draw the shear force and bending moment diagram, what is the steps we need to do? The first step is to identify the sections or the cuts we need to use. How many cuts we need for this beam? As we mentioned last week, we need a cut at the start of the beam and before and after any point load and at the end of the beam. Do we need more? We don't need more, so we have only 4 cuts for this section, for this beam, because from 1 to 2, we need a cut at the start of the uniform load and at the end of uniform load. So 1 and 2 are enough for this part, from 3 to 4 enough for the second part, okay? So we need only 4 sections or 4 cuts for this beam. The next step is to draw the guidelines. Okay. So under each section, we need to draw the guidelines. So this is our guidelines. And then horizontally is our data. So this is our data. And on this line, we will draw the shear force diagram. Okay. So if we start with section 1, what is the shear at section 1? Section 1, cut the beam to 2 bars, this part and part from left and part from right. So shear at 1, Q at 1 or V at 1 will be the reaction, which is 14.5 kilonewton. So the shear at 1 is the force going up, so we go up with the force, and the value is 14.5 kilonewton. Okay, and we said before, for shear force diagram, above the datum positive, below the datum negative. So from 1 to 2, the shear at 2 will be the shear at 1, which is positive 14.5, minus the uniform load in this part, which is minus 18, because the load going down. So this gives us minus 3.5 kilonewton. So the shear at 2 is negative 3.5 kilonewton. Negative means below datum or above datum. Below datum. So the shear at 2 is 3.5 kilonewton below datum. From 1 to 2, we connect them with a straight line. So this will be our line. Okay. Now we go to the next section. What is the next section? Section 3. From section 3, we have Q3. Q3 will be Q2, which is negative 3.5, minus 10, because 10 going down, so we reach minus 13.5 kilonewton. So the shear at section 3 is negative 13.5. So we go down up to 13.5 kilonewton. Okay, then from 3 to 4, Q4, we have Q4. The shear at 4 will be Q at 3, which is negative 13.5, minus the uniform load in this part, which is 6. So minus 6, so we reach negative 19.5 kilonewton. Negative means below datum. So the shear at this point will be 19.5 kilonewton, and we connect these 2 points with a straight line. Okay. After section 4, as you see, we have the reaction going up 19.5. So we have the reaction going up to 0. So the reaction will close our diagram. So we start from 0 and end at 0. Okay. So now we start at 0 and then end at 0. This shear force diagram, this part is positive because it is above datum. This part is negative because it is below datum. Okay. What is the next step? The next step is the moment diagram. So we finish the shear force diagram. Then we go to bending moment diagram. So we need to draw a datum for bending moment diagram. This is our datum. And we will draw the bending moment diagram on this data. How can we draw the bending moment diagram for this beam? Last week we said that the moment at any section equal to area of shear at this section. Okay, so if we want the moment at section 1 here, what is the area of shear at section 1? The area of shear at section 1 is 0. So M at section 1 equal to 0. M at section 2 equal to the area of shear at section 2. At section 2, this is section 2. This is section 2. So we can calculate the area from left, these two areas, or the area from right. Which area we can calculate, left or right? The area from right, from left, we don't know this coordinate or this dimension. This dimension is missing. We don't know it. So we cannot calculate from left. We need to calculate from right. What is the area? This is the area shape is trapezoidal. What is the area of trapezoidal? The area of trapezoidal, if you have a trapezoidal, you have two bases and height. If height h and two bases x1 and x2, so the area of trapezoidal equal to x1 plus x2 divided by 2, average base somewhere here, and multiplied by or times h, which is the height. So if we have a look here, what is the two bases we have? This is the first base. Let's say x2, and this is the small base, which is x1, and this is the height. So this is trapezoidal, and this is the two bases, x1 and x2, and the height is h. So if we apply the area of trapezoidal formula, if we apply the area here, this area, so we have 13.5 plus 19.5 divided by 2 multiplied by the height is, which is 2. So this two together is 34. Multiplied by 2. So the moment will be 33 kilonewton meter. This moment is positive or negative? This moment, the area of shear is negative, but because it is calculated from right, so the area should be positive. As we mentioned also last week, the shear, if you calculate the shear from right, it is negative, or you have to reverse the sign. So if it is negative, you have to convert it to positive. So because the shear area is the area of shear calculated from right, so we have to give the moment a positive sign. And also we said last week that the bending the rule of bending moment above datum is negative when you draw the bending moment diagram. Above datum negative, below datum is positive. So where to put this 33 kilonewton? Below or above datum? Below datum. So the area here is, the moment here at section 2 is 33 kilonewton meter. Okay. What is the next step? The next step is how to connect point 1 or section 1 and section 2. Because we have a uniform load between section 1 and section 2, so we have to connect them with a parabola. Okay, so I will draw a line here. And this line, straight line we said before, need to be dashed because this is not our drawing. So this is only a guideline to draw the parabola. So this this is a guideline. Then we have to hang a parabola. So the moment here in this part will be a curve like that. You can draw it with a curve here. Okay. So this is the moment here. And this part is a curve. And we said before, this curve is called second degree parabola. So this is the moment from 1 to 2. What is the next section is section 4. If you take the cut section 4 here, what is the area of shear at section 4? At section 4, you can calculate from right, no area from right. So the moment at section 4, M4 equal to 0. So the moment here is 0. How can we connect section 2 and 3 with section 4? From section 3 to 4, we have also uniform load, so we have to connect this 2 points with a line, a straight line, and this line should be dash line because it's not our moment, and then we have to hang a parabola. So this is the moment shape. From 1 to 2 and from 3 to 4, both are curves because we have a uniform load. So the moment, if the load is uniform load, so the moment should be curve or parabola. What is the sign of this moment? Because it is below datum, so this moment is positive. Okay. Do you have any question for this drawing? Any question? Okay. So the next requirement, I will keep this one because we need the drawings. So the second requirement is to locate the maximum moment. From the drawing, where you can find the maximum moment? The maximum moment will be at the point of zero shear. So if this zero shear, so if you go down to the moment, this should be your maximum moment, Mmax. So if we find the dimension to this point, so we can find the value of Mmax. We can give this dimension, as we mentioned before, x or x1, whatever. So x, this is the distance. And if we get x, so we get the location of maximum moment. So you have to know that M maximum, the maximum moment, located at point of zero shear. So at the zero shear moment, at the zero shear point, the moment is 0. Why? Because we said before that the moment is the integral of the shear value. So to get M max, you have to calculate the differential of Q, the function, and equalize it with 0. So if you equalize the function q with 0, and you get m max. So from this rule, we have to know that the zero shear point is the location of the maximum moment. Okay, how can we do this one? How can we do this part? To do this part, I will open another page. So to get MMX, we have to get the zero shear point. Okay, if we go to the drawing, this is our beam. This 10 kilonewton, 3 kilonewton per meter, and we consider this one 18 kilonewton, and here 6 kilonewton. The dimension here is 6 meter, 2 meter. The reactions are The reactions are 14.5 and 19.5 kilonewton. Okay, to get the zero shear point, we need to assume that the zero shear point at a distance x from point A. So we assume this is our zero shear point at x distance, and I will get this part out here. So if we get this out, so we have point A, the reaction 14.5 kilonewton, and some uniform load here. And this section, let's say this section XX. At section XX, we assume that we have shear, and the shear value is equal to 0. Okay, so how can we get this X? To get this X, the first thing is we need to concentrate the load in this part. How much is the resultant of the load in this part? We only extract a part X from the uniform load. So is the resultant 18 or different value? The resultant of this load should be 3 is the uniform load value multiplied by the distance, which is X. So the value of this uniform load is 3X. So at the zero shear point, what is the forces cause shear? We have two forces cause shear, 14.5. So we have at the zero shear point, we have 14.5 kilonewton going up, so positive, minus 3x going down should be equal to 0, which is the zero shear. Okay, so from this equation we can find that x equal to 14.5 divided by 3. From this equation we find that x equal to 4.8333 meter. Okay. Yes, thank you, Gong. So x, the value of the zero shear point is 4.8333 meter. Okay. If we go back to the drawing of our shear, I will draw quickly here. This was our guidelines, and this was our shear force diagram. So this was 14.5, here 3.5, 13.5, 19.5. Okay, so this positive, this negative, negative. So this is our shear force diagram. So the value of zero shear at the point of zero shear at a distance of 4.8333 meter. So we get the location of the shear of the zero shear. How to find, or the maximum moment? How to find the value of the maximum moment? If we draw the maximum moment again, this is our bending moment diagram. We set the value here 33 kilonewton meter, and I hang a parabola in this part and also connect this with a dash line and hang the parabola here. Okay, and we said this is positive moment. So the maximum moment at this point, which is this value mmx. Can you find mmx for me? I will delete this part. So now we know location of mmx between brackets zero shear, because this is a point, equal to 4.833 meter from support A. The next requirement, or the other requirement in this part, is value of mmx. How can we find the value of mmx? As the previous steps, to find the value of mmx, you have to calculate the area of shear at this part. So mmx will be area of shear at the point of zero shear. So at this part, where is the area of zero shear? Where is the area of shear? This is the area of this triangle. Can you find the area of this triangle? So mmx will be equal to, can you find the area of mmx? The value of mmx. The value of mmx will be this area, which is half the base, which is 4.8333, multiplied by the height of the triangle, which is 14.5. From this formula, we can find that the maximum moment is positive 35 kilonewton meter. So the value here is 35 kilonewton meter. So this is the maximum moment value, 35, and this is the maximum moment location, 4.833. Okay. Do you have any problem with this type of questions? So in this question, it is similar to the last week question, but we add another requirement, which is location of maximum and location and value of maximum moment. Okay. Do you have any question for this one? Okay, for the marks, I will send you the mark for this quiz and the previous quiz during the next week. Okay. Now I will shift to the next questions. Next question. So this question is similar to the question I have just solved. Can you see the difference between them? Can you tell me what is the difference? I will put it here. Can you tell me what is the difference between this question and the previous question? The difference is this part. No uniform dead load for this part. Okay, so it is the same dimension, same values of load, and same support, but the only difference is no uniform dead load between B and C. Okay, so this is the only difference. for this part. So I will give you some time to try this one. We'll give you up to 4:30 to try this one. And as a tip from me, I will give you the value of the two reactions here to just make it shorter for you, so you don't have to calculate the reaction. So this value of the load here is 18 kilonewton. The moment value, the reaction are, just a second. Thirteen 13.75 kilonewton, the reaction at A, 14.25 kilonewton, the reaction at C. Okay, so please try this one, and I will have a look on your trial. Okay, good luck. Okay, I will do it with you. So for this one, we have same problem, but only the uniform load is not existing between B and C. So for this beam, how many cuts we need? We need cut at A. So this cut 1, before and after B, the point load. So cut 2 and cut 3, and cut at 3C, which is 4. So we have 4 cuts, and this is our guidelines to draw. The shear force diagram and bending moment diagram. This is our datum. Okay, so to draw shear force diagram for this beam, at section 1, what is forces causing shear at section 1? This cut is here, section 1, so the shear force diagram will be the reaction, which is 13.75. So I will go up to 13.75 kilonewton. From section 1 to 2, we have go down 18, so 13.75 minus 18, so we reach 4.25. So here we will go up to 425 below datum, because it will be negative, and we connect them together with a straight line. This part of shear diagram will be positive because it's above datum. This part negative because it is below datum. From 2 to 3, we have 10 kilonewton going down, so we will go down 10 kilonewton up to 14.25 kilonewton. From 3 to 4, we don't have any loads, so the shear will be constant, 14.25 kilonewton. Okay, then after section 4, we have the reaction going up 14.25, so we reach 0. This part is negative because it is below data. Any problem with the shear force diagram? If you compare the shear force diagram in this example and the previous example, so the only part different is this part, because no uniform distributed load. Okay, this part, the shear is straight, not inclined line. Okay, the next step, The next step is to well, guys, I don't know what happened here. So the next step is to draw the bending moment diagram. How can we draw the bending moment diagram? The first step is to draw the datum. So our datum will be also horizontal here. Okay. And we will draw bending moment diagram for this part. Okay. Just remove this one. Okay, now how can we calculate the moment at section 1? At section 1, this is the section. So how much is the area of shear here? So again, to remind you, moment is equal to area of shear. So the area of shear diagram at 1 is 0. So the second section is section 2. At section 2 divides the beam two parts, section 2 left and right. Can we calculate the moment from left? No, because we don't have this dimension x. So we cannot calculate from left. So we have to calculate from right. What is the area of shear diagram from right? This is our section here. So the area of shear from right will be the area of this rectangular. So the moment at section 2 or 3 equal to 14.25 . Okay. So the area will be 14.25 multiplied by the distance, which is 2, equal to 28.5 kilonewton meter. Okay. This area is negative, but because we calculate from right, so the moment will be positive. So the moment is positive 28.5. The positive moment is below datum, so I will put the moment here, 28.5 kilonewton meter. Okay, from section 1 to 2, we have uniform load, so I will connect with dotted line, and then hang the parabola. So this part is positive. The moment at 3, section 3, sorry, section 4. So the area at 4, this is the area at 4 from right, no area from right. So the moment at 4 equal to 0. From 3 to 4, we don't have any uniform load, so we connect with a straight line. So the moment in this part is straight line. If you go back to the previous example, this is the only difference between the two diagrams. Here, a straight line. In the other problem, in the previous problem, the moment was curve or parabola. So this is the two differences. Different number one is the shear is constant line or horizontal line, and the moment diagram is straight line, not a curve. Do you have any problem with the drawing? Any problem with the drawing? Okay, now we go to next step. Next step is to find the maximum value of moment. How can we find the maximum value of moment? Okay, how can we find the maximum value of moment? Just open a new file. So how the next step is location and value of MMX. Same requirement as previous example. This example again, we have the beam, same beam. Two supports. We have reaction here, 13.75, 0. Uniform load up to here, 10 kilonewton, 3 kilonewton per meter, and 14.25 kilonewton. The dimension are 6 meter, 2 meter. We concentrate the load here as 18 kilonewton. Okay. To get the zero shear, to get the location of maximum moment, we said before that MMX located at zero shear point. To get the zero shear point, we have to assume the zero shear point at section here. Let's say section XX at a distance X from support A. Okay, if we take this part out, so we have this part out here, 3 kilonewton per meter. The reactions are 13.75 kilonewton. This is our section XX. When we cut here, we have shear value should be 0 because this is the point of zero shear. We concentrate the load here as 18 kilonewton. So this is the value of, is this 18 correct? No, we said before, this is the wrong thing you can fall in. So this value, this distance is X. The dimension is X. So the value of the moment is 3X. So at zero shear point, to apply the equilibrium equation, we have 13.75 going up positive minus 3X going down should be equal to the zero shear. So from this equation, we find that X will be equal to 13.75 divided by 3 equal to 4.58 meter. So this is our location of maximum moment. If we again draw the moment and the shear diagrams, this is our shear diagram. This is our guidelines. The shear diagram here was 13.75, here 4.25, 14.25, and 14.25. And we connected together with a straight line, this negative, this positive, this our shear force diagram. So the shear force, the zero shear moment is here at distance of 4.58 meter. So the value of maximum moment MMX will be area of shear at zero shear point. How much is the area of shear or MMX value? MMX value will be the area of this yellow triangle, which will be, the area will be 0.5 half, the base is 4.58, the height is 13.75. We get the maximum moment as 31.5 kilonewton meter. So if we go back to the moment drawing, we have calculated this value as 28.5 kilonewton meter. We connect this part with a straight line. So this part with a straight line here. And the other part, we connect it with a dotted line, and then we hang our parabola. So this all the moment positive. So if we go down with the point of zero shear, so this is our maximum moment value, max, which is 31.5 kilonewton meter. Okay, so this is the maximum moment value, and this is the maximum moment location for the two examples. Do you have any question for this part? I also want to show you the answers of the tutorial questions. If you have a look here, this is the first one. The first one was uniform load over the whole span. So this is the answers. The shear diagram, bending moment diagram, and the value of moment max 35. Just for the first question. For the second question, almost same question, but only no uniform load between B and C. So this is our shear diagram, and this is our bending moment diagram. The value of max here is 31.5, and the location is 4.58. Okay. Do you have any problem with this one? With this